Speaking specifically about the capacity of a telescope to collect area, something we could call the radiation collective power, or RCP, as I've called it in the lecture notes and here, is essentially the capacity for a telescope to capture photons. If you have a larger radiation collecting power, we'll be able to say fainter fluxes. And this essentially just depends on the area, and because the area for most telescopes will be the area of a circle, we're looking at something that depends on the diameter squared or the radius squared. And this obviously implies that if you're comparing two telescopes and the ratio of their radiation collecting powers, you're essentially looking at the ratios of their radius squared. It also follows that every time you double the size of the telescope, we're actually increasing its collecting power by a factor of 4. This is one of the main drivers for making telescopes which are larger and larger, because every time you gain by a factor of 2 in area, you're actually gaining by a factor of 4 in collecting area. But it's important to point out that every time you actually double the size of the telescope, the cost will go probably more than a factor of 4. So economic costs are also a consideration. The other important thing that we really should consider, and we'll see how this unfolds, is resolution. Resolution will be typically measured in this delta theta, and it's essentially the capacity to distinguish two sources when they get really nearby. So this resolution delta theta is the smallest angle at which you can still see two sources before they actually blur just into one object. This affects the capacity to distinguish essentially between these two different sources, or sometimes components of the same source. So you don't have to actually be dealing with two separate sources. Sometimes it's about looking at the details. This is typically quoted in arcsecond. You've seen an arcsecond is 1/3600 of a degree, and it's given as an angle. And we'll see that as a consequence of diffraction, as light goes through some aperture or a telescope, the resolution will be proportional to the wavelength that you're observing divided by the size of your aperture. And this means that if you're looking at really long wavelengths, you really require a very large aperture for diffraction not to be limiting you and to not kill your resolution completely. In practice, what does it mean to have low resolution versus high resolution? And perhaps the pictures behind me show this very well. This is an image, or actually two images, of the same galaxy, one of them taken in low resolution, of a resolution of about 4 arcseconds. So you can see here, delta theta is 4 arcseconds. And the image on this side has actually been taken with much higher resolution of 0.5 arcsecond. And perhaps the most obvious thing is that even though it is the same object on left and right, you will be able to see the details with much sharper contrast over here, especially if you're looking at structure in the spiral arm, perhaps structure also at the bulge of the galaxy. You really can't see it here, but if you turn to the much higher resolution, you can start to distinguish. So things that in the low resolution will look just like a blob will start to actually split into multiple sources. And this is one of the main drivers for having telescopes with really good resolution. So we can understand the details and actually realize and study different structures and objects instead of just thinking that it is a single object.